Oh, can you hear me?
Yeah, I can hear you.
Oh, okay. So now I can start, right?
Yeah, sure.
Okay. Sorry. Yeah, I forgot to the turn off mute. So let me start again. So thank you very much for giving me such opportunity to give a talk at the Consciousness Club. So I'm Kazuhisa Shibata from Riken Center for Brain Science, and today I'm gonna talk about the plasticity work that I had done like past 20 years. And before starting the talk, so let me briefly advertise the new hiring in our center, the Riken Center for Brain Science. So now we are hiring the 3 additional new team leaders in the subsequent, the following 3 categories. One is disorder research, and the other the human cognitive function research, and macaque, the brain research using macaque. And the deadline is November 13th, 2020. And especially I'm in the human cognitive function research team. So the one advertisement is that we will have the 70 magnet in weekend in the next fiscal year. So that allows us to measure the final spatial resolution activation and the higher SNE ratio, and that allows the new analysis such as like layer-based analysis. So that is really exciting. So please, everyone, please consider the applying to the position. So let me briefly about my lab that started literally a year ago, October 2019. So now there are 4 postdocs, the researchers. Oh, so the one is coming next March, and 3 technical staff who help doing experiment, and 1 assistant. So which is the good size, and the lab's interest or mission is to clarify roles of conscious and subconscious processing in higher brain functions. So previously, before coming to Weekend, my main focus was on subconscious processing and basic cognitive functions such as the perception of elementary visual features. But now that we'd like to extend our focus to the conscious processing and the interactions between conscious and subconscious processing, and investigate how the higher cognitive functions arises through the interactions between conscious and subconscious processing. So I will not really talk about the ongoing work today, but now there are many exciting projects which is underway. And today's topic, today I will talk about the visual perceptual learning research that I have been involved in the past like 15 or 20 years. So the visual perceptual learning, VPL for short, is defined as long-term increase in visual performance as a result of visual experience. So let's assume that you are asked to do the task, the orientation discrimination task, with this kind of gabor patch, and you have to tell the orientation. And when the signal to noise ratio of the stimulus is higher, your performance would be decent. But if the signal to noise ratio of the stimulus is very low, like left one, so although there is physically there is a orientation component in this stimulus, but you hardly see it. In that case, your task performance is pretty bad, poor. However, if you are trained with this task, for example, for 10 days, your performance would be much improved. And this improvement typically lasts for weeks or months. So this is the visual perceptual learning. Oh, by the way, let me know whenever you have a question. And please feel free to interrupt. All right, and one important and significant question in VPL research is how do we know what to learn? So the visual system needs to be sufficiently plastic for VPL to occur, to adapt to the environment. On the other hand, it also needs to protect existing visual perceptual learning from being destroyed by new but unimportant experience. So this problem is called plasticity-stability dilemma, which was proposed a long time ago, like 30 or 40 years ago. And it's old, but still very significant problem. And based on this kind of thought and endeavor in the past 30 years, this problem is now translated and re-termed as continual learning in the AI research. So it's also important for AI research. So today I will specifically talk about the visual perceptual learning and the plasticity stability dilemma. Especially the discovery from the two the great researchers, the professors Takeo Watanabe and Yuka Sasaki. So that they did a bunch of interesting and important work in this topic in the past 20 years. And they are also my mentor when I went to US, the Brown University and Boston University. And this 20 years of work and the 20-year period also overlap with my growth period. So at 2003, I became a grad student at NICE and ATR and joined Takeo's lab 2009, and back in Japan 2016, and then joined Riken CBS last year. This is kind of my review of this past 20 years, the 20 years of exciting period. So there are two main topics. First one is role of attention and reward in visual perceptual learning. And the other is the roles of passage of time and the training amount in visual perceptual learning. All right. Okay. So first one, so attention and reward. So the roles of attention in visual perceptual learning had been extensively discussed in 1990s. So, and then there's the bunch of experiment has been done. So let's assume that you are in an experiment, and on the center of the display, there is a fixation point. So please keep fixating the center. And on the left and right sides, there are the orientation stimuli. And you are asked to pay attention to the left stimulus, and then asked to report any changes in orientation. So the left stimulus is defined as task-relevant stimulus because it's attended in the task. And the right side, the right stimulus is defined as task-irrelevant stimulus because it's not attended. And then trial by trial, there is some changes in these stimuli. So in terms of the exposure, you are exposed to the changes in stimulus on the left side and right side. So in terms of the exposure, they are identical. But the attention is different. And in such a case, we typically observe the visual perceptual learning on the left hand, the attended task-irrelevant stimulus, but no perceptual learning occurs on the task-irrelevant and the unattended stimulus. Okay, so this is a basic observation in 90s. So it seems like the dilemma is already solved. So attention enables visual perceptual learning of task-relevant and important stimuli, while the attention prevents visual perceptual learning of task-irrelevant and possibly unimportant stimuli. So attention can reconcile plasticity and stability. So it's a good solution for the plasticity stability dilemma. So it's all set. But there's a problem. So under the task-relevant learning framework, we only learn what we think to be important a priori. So how can we learn what we are unaware of its importance? That is the big problem. So let me discuss the problem in detail. And that problem calls for or needs the poses the need for task irrelevant learning. So what is task irrelevant learning? So let me explain. So assume that you are a hungry tiger here, very hungry, and looking for the rewarding target, which is a food like a rabbit. So the rabbit is a task relevant stimulus for you. And let's say behind the bush, here is a rabbit, and rabbit moves. And then now you identify the rabbit and you get it. Okay. So, and at the same time with the rabbit movement, the bush will be slightly moved, right? So there should be the subtle motion of the bush. And also that motion will make a sound, weak raster. So although these raster and the bush motion are task irrelevant stimuli, so these task irrelevant stimuli predict the appearance or the rabbit. So if you can become the sensitive to these task irrelevant stimuli, so your next hunt will be much easier. However, with the attention-gated learning framework, you will only learn to see rabbit, but not task-relevant stimuli, here the bush motion and the rust sound. So there should be it would be really helpful for us to have the task-relevant learning mechanisms. Okay, so let me explain the series of studies that show the mechanisms of task-irrelevant visual perceptual learning. So first one was published in 2001. And the question is attention necessary for visual perceptual learning? For preparation, let me introduce one specific visual stimulus, which is called random dot motion. So the random dot motion consists of the tons of white dots, in this case, thousands of dots here. And on the left side, it's called suprathreshold motion, 50% coherence. So that means 50% of dots are moving to the moving rightwards, and the remaining 50% of dots are moving randomly. So you can clearly see you can clearly see the dot motion here, I hope. Although this is the Zoom broadcast. So, and the motion is very clear, so that this is suprathreshold motion. However, on the right side, so only 5% of dots are moving to right side. So you can't really see the rightward motion here. So although the motion energy is going to the right, the bias to the right, so physically the motion is rightward, but you cannot really see it. So it's subthreshold motion. And we use that motion in for the task relevant visual perceptual learning. So in the testing stage, before and after the exposure training stage, the visual sensitivity will be measured to the various different directions. So the coherent motion will be presented very briefly, and you will make an answer about the presented motion direction. So that kind of the performance for the motion direction will be measured before and after the experiment, the training. During exposure, your task is to identify some characters in the stream of letters. In this case, there will be 10 letters within 500 milliseconds. So it's really quick. And then eight letters are colored in black, and only 2 letters are colored in gray, light gray. And your task is to identify the light gray letters. And the random dot motion is also presented as task irrelevant on the background. And this motion is sub-threshold 5% motion. So you cannot really see to which direction motion is going. And also that you don't pay attention to this motion. Okay, so let's do some demo. Probably it may not work on the internet, but let's see it. So which letters are colored in gray. So it's very slow version. It takes two seconds. I hope you are ready. All right. So E and G, right? So this is slow version. It takes 1 second. Still E and Z can be seen, I hope, but probably not on the internet. And this is the actual speed. It takes 0.5 seconds. It's pretty quick. It's quick. So you even do not see anything on the display because of the time resolution. But probably if even when you directly watch this display, you may not really see the two letters. The letters are all the same, always E and G. So this task is really hard. So you have to pay your full attention to the central target, and you have no room for paying attention to the background motion. And the motion is also sub-threshold. So even when you pay attention to the motion, you will not see it. And so during the exposure stage, that usually take like 10 days or 20 days, you will be constantly exposed to one particular direction. And then before and after that, they tested whether your visual sensitivity to that exposed motion direction was increased. And it did. So the visual perceptual learning, significant visual perceptual learning was found only to the exposed direction. Although you did not pay attention to that, and it's completely sub-threshold, so the subliminal, the learning occurred to that direction specifically. So it's a task-irrelevant visual perceptual learning. All right, so the task-irrelevant visual perceptual learning was found. And the next question is task-irrelevant visual perceptual learning really passive and occurs exposure-based manner? That was published in 2003. So the experiment is very, very similar with the previous one, but this time whenever the letter switches to the different letter, the motion direction always switches. And one trick is that the target letters always paired with one specific direction, in this case upward. However, overall, the 4 different or 8 different motion directions are presented in the equal frequency. So if the task-irrelevant visual perceptual learning occurs in an exposure-based manner, purely passive, in that case, the VPL should occur in all motion directions presented. However, if it is not really passive, let's say related to the identification of the target letters, let's call it the event-related learning hypothesis. In that case, task-irrelevant visual perceptual learning should occur in a specific direction paired with task target. And the experiment supported, the results supported the second one. So the learning occurred specifically to the motion direction that was paired with the targets. So the event-related learning hypothesis was supported. And what is that? So still, it is really puzzling why it occurred. The one possibility is that your sense of success to identify the target makes some reinforcing signal, and that reinforcing signal makes the task-irrelevant perceptual learning to occur. In that case, the task-irrelevant visual perceptual learning should occur only when you successfully recognize the target. Okay, So they take advantage of the phenomenon called attentional blink. So let's say this is the stream of letters changing very rapidly, and task target T1 occurs here, and then the second target occurs within 200 milliseconds after the first target. In this case, you hardly see recognize the second target because the attention is attracted to the first target, and you need some time to get recovered. In that case, your recognition performance for the second target will be extremely low. And they use this phenomenon for the task-relevant perceptual learning. So let's say the motion direction to be learned is presented only with the second target. And for some, in some condition or some subject group, the second target was always presented 20 milliseconds after the first target. So in that case, recognition performance would be always very low. However, target is always paired with the one particular direction. And in the other subject group, the second target is always paired with the particular motion direction, which is the same, but the T2 occurs like 800 milliseconds after T1. In that case, T2 can be recognized with high performance. And they found that the task-relevant perceptual learning occurred only for the group without any attentional blink. So in that case, in this case, when T1 and T2 are separated in 800 milliseconds in time. So that means the successful recognition of the target letter is necessary for task-relevant BPL to occur. So based on this result, they made the psychological model of the task-relevant perceptual learning. So let's say you have some the task, and once you recognize the task target, the alerting or rewarding reinforcement signals occur, and it's diffusive. So that can facilitate the learning, both task-relevant and task-irrelevant feature. So even when the background task-relevant stimulus has nothing to do with the task-relevant target, such task-relevant feature can be learned based on the reinforcement signals. All right. So the study so far is just related to recognition of target. However, if that model is correct, there should be the case that the mere pairing of reward and stimulus is sufficient to lead to visual perceptual learning. So they tested that in 2009. So the experiment setting is like this. It's really crazy experiment. So the subject has the fasting, so no food or water 5 hours prior to each daily session. So basically when they came to the lab, they are so thirsty and very hungry. And the first author, the Kim Dong-ho, the Dong-ho used the water feeder, which is usually used for monkey experiment, to the human subject. So occasionally the water drop occurs, and then subject gets some water, just the 2 or 3 drops occasionally. And on the visual display, there are Mondrian colored stimulus is presented on the one eye, and in the other eye, the Gabor patch is presented. And with this kind of setting, what you perceive is the Mondrian colored patch. It's dynamic patch. So in this case, the suppression of the Gabor patch occurs. So you only see the colored Mondrian patches. So the Gabor patch is presented physically on your eye, and the information should be sent to the brain, but you will have no consciousness on it. And what they did is the subject task is just fixating on the center. and occasionally they got the water drop. On the vaccine, so the water drop is always paired with one particular orientation. And another orientation also presented, but it's not really paired with water reward. Remember, subjects are so thirsty, so the water is really rewarding. And they did this 20 days. So the subject had to really fixate on the center and they get the occasional drop for 1 hour in each day and 20 days in total. It's a crazy experiment. And before and after that exposure period, they measured the orientation sensitivity to the two orientations. One is orientation that was paired with the water reward, and the other orientation that was not paired with the water reward. And they also tested each eye separately. So one eye is trained, and the other eye is not trained. That means the other eye was not presented with the orientation stimulus. Okay, and they found the task-relevant visual perceptual learning specific to the orientation paired with the water and eye on which orientation was presented. Okay, so now the mere pairing of reward and the stimulus is enough to lead to task-relevant visual perceptual learning. However, there are some claims on that experiment, so that we made a step further. Probably in the audience, some may wonder that the stimulus, okay, these stimuli were weak enough, but yeah, if you are the kind of specialist of vision science, you know that sometimes you can see the stimulus. So the subject might have been perceivable. The stimulus might have been perceivable in some limited trials, while most trials subjects saw nothing. And such occasional perception caused visual perceptual learning to occur, because once subject can see the perceived stimulus, which is that can be just normal visual perceptual learning. Okay, then let's take out stimuli from the exposure stage. That was our approach. So if there is a stimulus, there is no stimulus, there should be no learning. However, by using some technique called decoded neurofeedback, we made it possible. So before the experiment, we can measure fMRI activity pattern that represent certain orientation. And during the neurofeedback training, without showing any stimulus to the subject, we can ask them to change their brain activation pattern, so that the activation pattern can become closer or more similar to the activation pattern, which is evoked by the presentation of the real orientation. And when the activation pattern occurs, we give them some monetary reward. So in this case, the reward and activation pattern were paired repeatedly, and we did this experiment for 10 days. And before and after the experiment, if the visual perceptual learning occurs specifically to that orientation, the target orientation, now we can say that the task-relevant visual perceptual learning occurs without the stimulus, or without the perception of the stimulus, and it did. So when we checked compared the visual sensitivity before and after the decoded neurofeedback training, we found the nice improvement, specifically to the target orientation. And this improvement was nicely correlated with the neurofeedback performance. So that means for some subjects, they are really good at the regulating their activation pattern in the visual cortex. and such subjects learn better in the visual sensitivity. All right, so now the model is strongly supported. So once the reinforcement signal occurs, the task relevant and task irrelevant learning both can occur. All right. So these findings arises the additional question. So what is the role of attention in VPL again? Because the reinforcement signal can facilitate the running of task-relevant stimulus and also task-irrelevant stimulus. However, remember, in the earlier experiment, they showed that attention facilitates the task-relevant learning and inhibit task-irrelevant learning. So the attention and reward seems to be contradicting to each other. So what is the interaction? Well, what is the role of the combination of attention and reward? So that question was addressed in 2008. So again, the random dot motion and the radar recognition experiment. So this time, like previous one, the task targets were always paired with the certain or the motion direction. But this time, one target was paired with suprathreshold motion, and the other target was paired with subthreshold motion. Okay, and they checked whether the task relevant running occurs to the suprathreshold motion and subthreshold motion. Okay. And this is what they found. Oh, sorry. This is what they found. So the task-irrelevant visual perceptual running occurred with subthreshold or parathreshold motion stimulus, so which is consistent with the previous experiment. However, they did not see any significant improvement with suprathreshold motion. So this result suggests that the attention suppresses task-irrelevant visual perceptual running of suprathreshold motion because it's salient enough. But when the background task-irrelevant motion is not salient at all, subthreshold, these stimuli are not really suppressed. So that's why the task-irrelevant visual perceptual running occurs. Okay, so if this kind of idea is correct, so for those who has weaker attentional ability should show task-irrelevant perceptual running even when the task-irrelevant stimulus is suprathreshold, right? So this is the prediction for the next study. So we recruited both younger and older subject. Older subject basically defined like the age above 60 or 65. So my memory is not so good. So and we replicated the previous finding with the younger subject. So the younger subject showed the task-relevant learning with the subthreshold motion or parathreshold motion, but no improvement occurred with the suprathreshold motion. On the other hand, elderly subjects showed the significant task-relevant visual perceptual running with suprathreshold stimulus as well as subthreshold stimulus. And it has been known that in the elderly participant, the elderly participant generally has the weaker attentional suppression. And we also measured the score, the attention score, selective attention score. In this graph, the higher means weaker attention score, weaker suppression. And the lower score means the stronger attentional suppression. And the y-axis showed the degree of task-relevant visual perceptual running, and they are nicely correlated. So that means that if your ability to suppress the task-relevant stimulus if your ability of the suppression to suppress the task relevant stimulus is weak, the stronger task relevant visual perceptual learning occurs, even when the stimulus is suprasessioned. So now it has been clear that the attention and the reward, the reinforcement signal by reward, has the distinct roles in visual perceptual learning. So attention facilitates task relevant feature, the learning of task relevant feature, while inhibit task relevant feature only when task relevant feature is inconspicuous, the very salient. And the reinforcement by reward can facilitate both task relevant feature and task irrelevant feature. So that is a kind of completed model of roles of attention and reward in visual perceptual learning. So the first part has been done. So do you have any question on the first part? So let me briefly check YouTube as well. No questions, okay.
Yeah, we will also have a Q&A sessions after the talk. So yeah.
Okay.
Yeah.
All right. So let me go to the next one. So roles of passage of time and the training amount. So I made some change in the question. So how do we know which to run? So in the real life, you may have to run different things at the same time or in succession, right? So let's say you are in the training with orientation A, and that training is immediately followed by the training on the similar but different orientation B. So in that case, so the two similar orientations usually share, or they are likely processed in the same neural circuit. There might be some contradiction. And yeah, which is really, it is really great if we can always run two things at the same time. But since learning is a dynamic process, we need sometimes take some time to one learning, take some time to make one learning get stabilized. So it is a consensus. There is a consensus that if you learn something, it takes time for that learning to get stabilized. It's like you get something new and you need to take it, put it on your stage, and you takes time, several like minutes or hours to move the new thing to your stage. And also there's the known process which is called re-stabilization. So let's say you learn something new and it's stabilized once, and in this different day, do you use that one again? The learning again, so that you use the learn technique again. In that case, that memory or that learning becomes fragile again, and it takes time to make it stabilized again. So it's like you have new things and you put in the stage, and when you use that, you need to put that one out from the stage and then put it back to the stage. It takes time, and sometimes that one gets destroyed. All right. So the learning is a dynamic process. So sometimes you cannot really learn two things at once. And there has been shown that there are two important factors. One is passage of time. The other is amount of training. So let me clarify step by step. So the first one is about passage of time. So the passage of time is necessary for visual perceptual learning to be stabilized. So that was tested 2005. So this is the task. So you need to fixate on the center, And on your peripheral, there are 3 dots. And your task is to report these 3 dots are aligned in one straight line or slightly disaligned. So in this case, the center dots are slightly placed to the right. So if you do that in the peripheral, it's extremely difficult. Maybe you can test it by yourself. Right, so it's very difficult. And okay, so if this task is trained like 5 or 10 days, in solo, you can run that task. However, let's say when you are trained with this task with a very similar task, in this case, the S1 is the task I described before, and the S2 is the slightly different task. In this task, you have to tell the 3 dots are aligned in a straight, or the center dots are slightly displaced to the right, or to the left, sorry. So they are very similar and conducted on the visual location. So, and without any blank between them. And let's say you repeated this 5 days or 10 days. In this case, the S1 is not learned. So remember, S1 can be learned in solo. However, if S2 training was done right after S1 training, so learning of S1 does not occur. So this is called retrograde interference. And what's interesting here is if you put 1 hour blank in between 2 training periods, the learning of S1 occurs. Okay, so that means this 1 hour blank is crucial. So the VPL of S1 became stabilized during this 1 hour blank. So time matters. And the next one is about the amount of training. So we showed that depending on the amount of training, the stabilization of visual perceptual learning can be switched. So in this experiment, we used the Gabor orientation detection task. And if you are trained with this task for 4 blocks, like 10 minutes, you will show no significant improvement. But if you are trained with this task for 8 blocks, like 20 minutes, you will show the nice and significant improvement. However, if we continue this training, let's say 8 more sessions, 20 minutes more, you will have no additional improvement. So let's say, let's use these 8 blocks of training in the first experiment. Okay, so you are trained with you are trained for 8 blocks with orientation A. Then within 30 minutes, the next training will start by using the slightly different orientation for 8 blocks. So in this case, the learning of the first trained orientation was nullified. So remember in solo that you can show the learning with 8 blocks of training. But if the 8 blocks of training on the different orientation, slightly different orientation was made, the first learning was disrupted. So this might be because that the visual perceptual learning of the first orientation was not yet stabilized and therefore overwritten by the subsequent training. So indeed, if we put 3.5 hours blank between them, the learning occurred for both orientations. And next, so let's get back to the solo training. So with additional 8 blocks of training, so we see no additional learning. So in this case, this kind of additional training is called overlearning because there is no additional learning effect. But back in 1885, the Hermann Ebbinghaus found the very interesting phenomenon, which is called the retention, the increased retention. So the overrunning makes the retention period longer. So that if overrunning occurs, you will remember something longer. And we thought that the stabilization of visual perceptual running can be increased by this kind of overrunning. So let's do that. So the first orientation was trained for 16 blocks now, and we put 30 minutes blank. And the second orientation was trained for 8 blocks or 16 blocks. So in that case, in neither case, the perceptual learning of the second orientation was hindered. So we interpreted this in the following way. So the visual perceptual learning of the first trained orientation is so stabilized, so strongly stabilized, that VPL of the second orientation is impeded. So this is pretty much different from the classic notion of stabilization, because the stabilization, once stabilization occurs, the both orientation should be learned. But this time, second orientation, the learning of the second orientation was disrupted. So we call it hyper stabilization. And yeah, like previous one, if we put the 3.5 hours blank, both orientation were learned. So stabilization occurred the 3.5 hours later after of the first training. So what is happening in the visual cortex? So to check that, we use magnetic resonance spectroscopy, MRS for short. That allows us to measure the concentration of glutamate, which is excitatory neurotransmitter, and GABA, which is the inhibitory neurotransmitter in the brain. And we measured this glutamate and GABA from the early visual cortex, which is known to be involved in the visual perceptual learning of the orientation. And we calculated the excitatory inhibitory ratio, the glutamate over GABA. So because the literature says the excitatory inhibitory EI ratio is closely related to the plasticity. Okay, so this is the result. So let's take the baseline, the pre-training MRS as a baseline, and we measured the MRS the 30 minutes late after the first training and 3.5 hours after the training. And if the 8 blocks of training, which is no overrunning, was conducted, the EI ratio changed in a positive manner, increased, and then 3.5 hours later, it gets back to close to the baseline. When the overrunning occurred, the opposite thing occurred, was observed. So right after the training, so EI ratio decreased from baseline in the negative direction. And then 3.5 hours later, it goes back to close to the baseline. So we observed the various things. One is the retrograde interference that shows the unstabilized visual perceptual learning. And as time goes by, 3.5 hours later, the perceptual learning has stabilized without overrunning. Okay, so the training makes visual perceptual learning very fragile and plastic state. And as time goes by, it gets stabilized. However, if training is too much, then overlearned, the visual perceptual learning is hyper stabilized. And this hinders subsequent training. But the same as the no overrunning, as time goes by, it's stabilized and went back to the baseline. So this is what we found with the MRS study. And finally, the passage of time, we found that the passage of time is necessary for visual perceptual learning to be re-stabilized, stabilized again. So as we discussed before, the learning is dynamic, and even after the first consolidation, if you remember or if you use the skill again, that becomes fragile. and it takes some time to make it re-stabilized. So we mimicked that experiment in the visual perceptual learning framework. So in day one, the training on the orientation A was conducted for 16 blocks, and that is consolidated within 3.5 hours. And then day two, subject came back to the lab and then did the task for 3 blocks to reactivate the once consolidated the visual perceptual learning of the orientation A. And right after that, the similar orientation B was trained for 16 blocks. In this case, after that, when we tested the performance of the orientation A, we see no visual perceptual learning. So that means the visual perceptual learning of orientation A was nullified due to the training on B right after the reactivation of the A. But if we put the 3.5 hours between the reactivation of A and training on B, so there are no disruption of the A learning occurred. So within the 3.5 hour blank, the visual perceptual learning of the orientation A was re-stabilized again. And we did the MRS study again. So, and we found very similar mechanisms for stabilization and re-stabilization of BPL. So once the reactivation of the consolidated visual perceptual learning occurred, the EI ratio in the visual cortex is increased. And within this time window, if we do the training on B, the visual perceptual learning of A was nullified. However, after 3.5 hours later, that was destabilized again. So we talked about, I talked about, that was the another role of the passage of time in visual perceptual learning. So this is the final slide, the summary of the talk. So we reviewed the roles of attention and reward and the passage of time and the training amount in visual perceptual learning. And the attention, with attention, we learn what we think to be important. And paired with reward, we learn what is the reinforced, even when the stimulus is task irrelevant. And time, so that we usually learn what is trained later time-wise, but time tells sometimes. So the time is necessary. The passage of time is necessary to learn 2 things. And the amount of training, so we learn by overlearning, we learn what is excessively trained. So this is it. Thank you very much for your attention.
Okay, yeah, thank you very much for the very beautiful sequence of the studies, Lisa. So yeah, we now move to the Q&A sessions, but let's see Slido. Yeah, no one has any post, so
No post.
Yeah, no question yet. But I think some people have questions. Should be, but if no one, let me very naively ask some questions. So so you mentioned relationship between attention and also the task irrelevant feature. So basically from the the talk, my understanding is the attention basically suppressed this task irrelevant feature on very early stage of visual cortex, a visual cortex. Is there any higher order kind of suppression on different brain regions, or just more specific to more visual cortex?
I see. So there's actually a very nice experiment on it.
Mm.
So let me show that. So actually, the task relevant signal is not suppressed. So at least for motion, task relevant stimulus is not suppressed at the stage of early visual cortex.
Okay. Yeah.
Oh, sorry, I might be wrong. So okay, so this is the experiment done by the Takeo's group. So it's a task relevant stimulus is here, and this is the main result.
Mm.
So let's say see the MT plus here. So when the motion stimulus is task relevant, the as coherence gets higher, the MT signal gets stronger. Okay,
Right.
and when the motion stimulus is task irrelevant, so with the higher coherence, the MT activity is weaker. However, if when it is sub-threshold, the MT's activity is higher. So although the attention can suppress the task relevant motion when it is conspicuous, the salient, when it is sub-threshold, the signal reaches the MT, which is regarded as higher visual cortex. Did I answer to your question?
Yeah, can you say that again? Like maybe I missed the point, I guess. So even okay. Sorry, even how can I say that? Like so. Sorry, even like the signal in the MD about like task relevant features are kind of responded, but doesn't affect the performance. Like
I see. It does. Sorry, so I skipped that part. It is that is really a great question. So this is the performance of the letter identification task. Okay, so when the task relevant motion is very salient, or when there is no coherent motion, the letter identification performance is higher. However, the letter identification performance gets decreased when the task relevant motion was parathreshold, especially when it is subthreshold. So that means some disrupting signal occurs within the visual area. Then that's why that their task relevant, the task performance is hindered.
Okay. Yeah. Okay. Yeah. Thank you very much. Yeah, I think I grasped the idea. Okay. Yeah. So any questions? Like so far, we don't get any question from Slido. So yeah, anyone from Zoom, you can ask a question directly, I guess. Maybe today a little bit everybody shy. Like usually, like we have a lot of people today. So yeah, I think. Oh yeah, okay. Someone Kawakubo-san like asked a question. So let me share through the Slido. Can you see the Slido? Slido. Maybe for the people who not understand the. Yeah, thank you very much for the great talk. like okay. Sometimes like older people, when we play with them, that some game together with them, they learn some games and are very more competitive than like younger people. But like, once like the game rule is changed, the like older people like becomes weaker. He has seen those kind of example several times. Can you explain that kind of phenomena through your models you in the talk?
Yeah, good question. It's really hard to answer this question. So the in the, as far as I know, in a general sense, the elderly people are not really good at controlling attention or switching what the suppressing the irrelevant stimulus, and that makes probably hard to keep up with the rule change. However, yeah, so as you said, the elders are, it does not necessarily mean the elders are not good at learning. So not in my model, but from the same laboratory, or yes, I involved in the comparison in the elderly and younger people, and in the subsequent study in their laboratory. So they showed the both elderly and the younger people can show the compatible amount of visual perceptual learning, but underlining the mechanisms, the brain mechanisms are different. So they measured fMRI and also the anatomical change using the diffusion tensor imaging, and it's really counterintuitive. But the younger subject, the changes are found in the functional activity in fMRI, and in the elderly people, they found the changes in anatomical structure, but not in functional change. So in a sense, it sounds like the elderly people has the more plastic brain, because usually after the critical period, once you become an adult, the less structural change occurs. But in this case, the elderly people show the stronger structure change. So the mechanisms of learning are likely different between the youngers and the elderlies.
Okay, yeah, thank you very much. And the next question from Julian.
Julian, from my lab.
Okay. Yeah, the summary of learning effects for BPL seem to mimic the kinds of factors that are important for learning more broadly. Does this similarity imply any shared characteristics between very basic perceptual learning and learning more broadly?
Great question. So yeah, so the question is okay. So is there any commonality between with other types of learning, right?
Yeah, I think so. Yeah.
Yeah. So this is another study.
Okay, I'll stop my sharing.
Okay.
Yeah.
All right. So it has been known that the visual perceptual learning and motor learning share so many components, and also the general memory mechanisms as well. So both visual perceptual learning and motor learning have the encoding period and consolidation period, or reactivation and re-stabilization period. So by studying the research on visual perceptual learning should have benefit for the other, domain of the learning. And what was the question? Summary learning effect. Yes. So the short answer is yes. So that there are some shared characteristics.
Sorry, yeah, sure. And maybe next question.
Hmm.
Okay, anonymous. Can we consider the responses same between the first block and the block of trials in the visual consciousness task, like backward masking or structured stimulus? Hmm. Sorry. Okay. Got it.
This sounds like very difficult to
Answer.
maybe, yeah. So that
Yeah. Okay. Yeah. Sure. I mean, there are sometimes like this touch system is not perfect, so maybe we can skip to the next question.
right.
Yeah. So could you explain more about neurofeedback in the context of the unconsciousness perceptual learning?
Okay. So I have some slide for that.
Okay.
So that the neurofeedback experiment was done in the 2 steps. So first stage was called decoder construction. So in the experiment, we presented the real actual orientations to the subjects and measured fMRI data from the early visual cortex. So that we switched the orientations and measured corresponding activation in V1, V2. And then after that, now we have the pairs of activation and orientation. So by using the machine learning technique, we can make orientation decoder. So based on the activity pattern in V1, V2, now we can guess or quantify the likelihood of the orientation. So basically, based on the new fMRI data, now we can say that, okay, so this activation pattern looks more like the activation pattern that had been evoked by this orientation, but not other orientations. So that it's one measure of similarity between the new fMRI data and the fMRI data that were evoked by orientations. So we use this orientation decoder in the neurofeedback experiment, which we call induction period. That takes 10 days. So during the induction period, we selected one particular orientation as a trend orientation or target orientation. So we have 3 orientations in this experiment. So, and then these are different in 60 degrees from each other. So the selected orientation was termed target orientation, and the others are called -60 and +60 orientation. And this is the visual display presented to the subject during the induction stage. So first, the fixation point gets green in color. So that means this is a cue for subject, and now the subject has to control or regulate their brain activation. And then after some fixation period, they have a feedback that tells subject how much their activation was good in terms of our criteria. And if their activation pattern was great, they get more money. So in the vaccine, what we did is this. So that we measured the early visual areas activation from V1 and V2, and then put the activation pattern into the decoder that we made before, and calculated the likelihood of the target orientation. So in this case, 30%. So the circle presented to the subject is small. So the subject, the monetary reward is smaller. However, let's say when it is 80%, they were presented with the larger circle, and they know that a larger circle means larger monetary reward. So this is the procedure of the neurofeedback experiment. And then before and after that, we tested subject in a psychophysical experiment. So they are asked to report the presented orientation and whether that orientation is target orientation or minus 60 or plus 60. But the subject did not know which one was target orientation. And then we found the nice improvement specifically to the target orientation. So that is the more details of the neurofeedback experiment.
Yeah, thank you. So yeah, we have more questions. Okay, anonymous. Sorry, like I have to share. Okay, right. Okay. So I want to confirm my understanding. If there is a training effect, is the threshold of the visual perception changeable in the experiment?
Yeah, it does. Yeah. We observed slight changes in threshold as well, but that was not huge.
Okay.
So yeah, I mean, it is not the case that during experiment the stimulus became supra threshold. That kind of things did not occur.
Okay. Yeah. Okay. So next one is from Ayumu. It seems there are a few individual differences about BPL, but are there any studies investigating individual differences of BPL ability?
Yes, it does. So the recent publication in PNS, it's not our team, but yeah. So the Zonlin Luz group measured perceptual the inter-individual differences and the inter-task differences in perceptual learning. And what interesting there was that the variation of the inter-individual differences can explain the inter-task differences in perceptual learning. So there are the subject-specific component can explain many things. So there is a systematic differences in the learning ability itself, and it might have the broader effect.
Right. Yeah. Thank you. Maybe we can ask later, like more details. But I also got the question from YouTube from Samejima Sensei. So yeah, can you see the post? Maybe we can. I have to check how it looks like.
I see.
Yeah.
ERS and neuroplasticity. Yes. So in our experiment, we found the disruption of the visual perceptual learning. I mean, we found the relationships between disruption of visual perceptual learning and changes in EI ratio. So when EI ratio gets down from the baseline, the hyperstabilization became stronger. So in that sense, the plasticity and visual perceptual learning were EI ratio and visual perceptual learning were correlated. But probably the Samejima-san's question is beyond that result. So he's asking whether there is the general. Sorry. So Riken has this kind of chime.
Like school.
Yeah, it's like a school.
But it doesn't make sense. Like 520.
520. Yeah. So it's hard to explain, but yeah, always the Riken's work is done. Yeah, 520. Anyway, so probably he's asking about the baseline EI ratio before training. And in our particular experiment, the sample size, I would say the sample size is not enough to show the inter-individual differences. I mean, the inter-individual differences of perceptual learning and also EI ratios. So what we found is the within subject to change, right? So we had 3 MRI sessions, and we found the correlation with the between changes. But in this case, it's not change. So the basic inter-individual differences of EI ratio, and we did not find the significant relationships between the baseline EI ratio and the visual perceptual learning. Probably if we have the more sample size, if we have more number of subjects, maybe possible, but yeah, we have no conclusion yet. And okay, mechanistic explanation, mechanistic. So I wondered what the neural mechanistic explanation means. So what we measured was the glutamate and GABA, and we have some correlation between perceptual learning and the glutamate GABA ratio. However, it's really hard to say go beyond with the MRS measure. So the MRS measures the concentration of glutamate and GABA, but that reflects the GABA and glutamate, both intracellular and extracellular. So it's a bit hard to connect the MRS result with the neurotransmitter result, so within soma. So so there's a kind of gap between them. So clearly we need the animal model experiment and the compare the MRS signals and inhibitory neurons, excited neurons activation. And actually, in my previous affiliation, the QST, some researchers are working on it. And we found at least partially the MRS measure and the inhibitory and excited neurons activation are correlated. So this is what we know so far.
Yeah, all right. Thank you very much. So yeah, we I think had all the questions from the Slido. So yeah, anyone can ask question from the Zoom. But yeah, I think maybe I might ask also very naive questions, but maybe make Samajon Sensei also kind of interested in like, is there any like mechanistic explanation of association with dopamine or things like that, like in a visual cortex? I'm not so sure, but seems yeah. Do you have any like relevance?
Right. Yeah. So the pharmacological experiment was not yet conducted. But yeah, in the independent group, other groups made some effort on it. So some group in Belgium had very interesting result after paired association between some stimulus and the reward. What was that? So by showing which is they used the paradigm which is very similar with the Takeo's paradigm. So after the paired association, they found the reward-related activation in early visual cortex. So that may modulate the task-relevant visual perceptual learning based on the reward. But I think the cellular mechanism is not really shown. In the auditory domain, there is, but in the visual domain, I'm not really sure.
Yeah.
So, yeah, in the auditory domain, the paired stimulation between the auditory cortex and the real circuit makes the huge change in the sensory map, the tonotopy map in the auditory cortex.
Oh.
So the kind of reward circuit really modulates the kind of perceptual learning in the auditory domain.
Yeah, that's just interesting.
Mm.
Oh, okay. Right. So yeah, anyone? So have you seen the people in Zoom? Like maybe Ayum-san, like.
Yeah, I know Ayum-san. And Aurelio was there, but he left.
Okay.
Hi, can I ask?
Yeah, sure.
So you say reward promotes the VPL, both task relevant and task irrelevant. And how about the punishment? So what happens if punishment is given?
Yeah. So so you are in Boston. So what time is it? Like
4 a.m.
Oh, night owl. Yeah, thank you for keep awake. Yeah, so the Ben Seymour's group recently published such kind of paper. So with the punishment, they can be with some the experiment they can be that they give some pain, and the pain discrimination can be improved with training. But it's not about punishment in the okay. It's the stimulus itself is punishment. Yeah. So I think in the motor domain, they say the such kind of experiment, the experiment compared the effect of reward and the effect of punishment. I'm not sure in visual perceptual learning yet. And the motor learning experiment was really interesting and very it's deep. So if you are trained with reward, let me explain the punishment first. If you are trained with punishment, your online performance is higher than the training with reward. However, your retention is weak. So with punishment, you learn fast, but you forget faster. And with reward, the online performance isn't very high, but you will remember it longer. So if there is a common mechanisms between visual perceptual learning and motor domain, maybe I would predict the same thing occurred in perceptual learning.
It's interesting.
Okay. Anyone? Interesting. Yeah, okay. Maybe a little bit like we started earlier than usual. So yeah, we don't have much like guests yet. But so yeah, so I think so far like you explained a lot of things like so far you did. But can you a little bit also like you have something you can show recent studies or something? Maybe not. But yeah.
Right. So it's so many ongoing stuff. One is about implicit memory, and especially I got excited with one interesting phenomenon. So let's say we can learn we can get the memory without knowing. So it's called instantial learning. So even when you don't have any intention to memorize things, occasionally you remember something without any awareness. That can be tested in various ways, and it is really well-known phenomena. But we recently found the two okay, so we can make the two different implicit memories in one experiment, and these two implicit memories can interact to each other without the outside of our consciousness.
Right.
And that kind of phenomena can be shown, it develops over time. So let's say you got that kind of implicit memory today. Tomorrow, your two memories will be fused in a very unique way. And the fMRI signals can capture the mechanisms of this kind of memory fusion. So it's unpublished work, so that it's really hard to say the details yet.
Yeah, sure. So,
yeah,
thank you for answering. Maybe it's very to see, but yeah, okay. Anyone from YouTube or? Okay, no one yet. Right. Yeah, we already kind of spent like 30 minutes for the discussion already, so we can of course stop from here. But yeah, okay. So right then, okay. If no one, then it's we can close the discussion stay. But thank you very much for the Shibata-san, like for the great talk, and I think it's very inspiring for the like very beautiful, I think, explanations about the task-relevant perceptual learning, and so before we close the talk, we let me a little bit advertise the next talk of the Consciousness Club Tokyo. So we're going to have a talk by Christian Sandberg from Aarhus University in Denmark on October 9th. So if you are interested in the talk, his talk should be related to some metacognition. So if you're interested in it, please check it out. I'll post the YouTube link and other stuff on my Twitter account. Thank you very much. Okay. All right. Thank you very much again for the and also joining this discussion and Zoom. Okay. So we are very excited to see your, I think, like unpublished work soon, maybe related to this. So okay. Thank you very much again. Okay. See you everybody again soon. ありがとう